Ryan Wright is the CEO and founder of a company called ThatDot and the founder of an open source project called Quine. Quine is a real-time graph. Notice I didn't say database. You kind of wanted me to, but that's not how Quine describes itself. A lot of fascinating things to dig into here. Graph analytics in real time at scale, very thorny problem. And it's fascinating how Quine solves them. And Ryan does a great job explaining some of the solutions under the hood. So can't recommend it enough. Listen to this whole episode. And before we jump in, keep in mind the Real-Time Analytics Summit is coming up soon. It's May 7th through 9th in San Jose, California. You can go to rtasummit.com to register. And if you use the code RTAPOD30, that's RTAPOD30, you get 30% off your registration just for being a listener to this podcast. What a deal. Check it out. And now let's listen in to my conversation with Ryan. Hello and welcome to another episode of the Real-Time Analytics Podcast. I'm your host, Tim Berglund, and I'm joined today by Ryan Wright. Ryan is the founder of a company called ThatDot, and we're going to talk about streaming graph analytics. Ryan, welcome to the show.
Thank you, Tim. Glad to be here.
I am excited to talk about this topic. I've not really delved super deep into graph databases, but played with them. And I'm very interested in the intersection of them and real time, realizing that I'm biasing the discussion. I said graph database. I don't even know if that's what we're talking about today. So tell us about ThatDot and Quine, and let's just kind of break this thing down.
Sure. So ThatDot is a young company behind a new open source project called Quine. Quine is the world's first streaming graph. And we try to stop just short, actually, and say not graph database, but a streaming graph.
It feels like there's a word you're not saying when you say that. Yeah, that is intentional, and I love it.
For a long time, like graphs have meant graph database. And there have been a lot of interesting technologies and trailblazers who have really done a lot of work to create that space and create a lot of great tools in the space for working with data and thinking about connected data and really bringing that to the surface as a graph. But unfortunately, that has also kind of brought, say, 50 years worth of technology baggage with it to say that, well, if you're going to work with a graph, it's got to be in this database paradigm. But the world's kind of shifting away from just this static database paradigm. It's kind of headed in the direction of data in motion and fast-moving data and analytics that we have to do while it's moving. And so for a long time, graph databases have kind of built their own ceiling to what they can accomplish, because most architects I know would say, graph database, it's cool, but it's too slow to use in production. So we can't really have that as a bottleneck in our data pipeline. Certainly in any real-time application, it just wouldn't, nobody thinks that. There's, I'm sure, ways to ingest from Kafka, et cetera, but they're not built for that. Yeah, so that's kind of the evolution that graphs have been going through. As they started as this static repository where you could query and visualize data in its connected form, so as a graph, and then plug them into a source like Kafka and consume it from a stream. You can still build a graph from the stream. That's great. It's a good step forward. But the limitation on that always kind of ranged in hundreds to maybe thousands of events per second. And anybody who's really working with streaming analytics and real-time analytics, like those are really small numbers. And if that's where your ceiling is, then that's, kind of a non-starter. And so the fallback position has been that teams build their own graphs. They build it in the infrastructure and then in the pipeline. So connecting microservices together, so data flows through different components in a microservice. And through that, they build a graph, like as a track that the data flows along. And what it takes away is the expressive ability to think of data as a graph. I want to stop you there for a second. It takes away the expressive ability to think of the data as a graph. So don't lose that statement. That's a big statement. But building the graph, do you mean that graph is expressed in the architecture of the system itself? Yeah, exactly. And not in the data? Okay, so they allow that graph as data flows through services as
sagas are worked out or whatever that happens to be. You've got these reactive microservices consuming from Kafka topics or something.
Yep.
That expresses a graph. You're saying so we kind of let ourselves do that, but
yeah, and it's usually a directed acyclic graph. So it's kind of flowing around, but it's all going in the same direction, and it ends at one place and doesn't loop back
somewhere
on itself. Yeah.
Yeah.
But what if you need to loop back on yourself? What if you need to think about, circles in your graph or in your data, about, the diamond pattern or things that get formed by loopbacks in the data, essentially. And so being able to represent those and process those on a stream in real time becomes really tricky if you're trying to build a data pipeline that way. And so this notion of graphs has kind of been lingering around, on the sidelines for a long time because they're a powerful way to represent data, and they show up in pipelines in this directed form. But the whole capability of this to be able to say data itself is connected, and it's useful to think about that structure and work with that structure live on data as it's moving. That's always been just out of reach for a long time because we haven't been able to scale graph computation very well. That's where Quine comes in. So that's what we've been trying to solve for the last 9 years. So
Quine is the open source project.
Yeah, exactly right.
Yeah.
So it's all at quine.io. Quine is meant to be the world's first streaming graph. So it plugs into these streams, basically sits in between two Kafka topics. Okay. So data streams in, and critically, data streams out. And in the middle, you can actually use a graph to start connecting data together, have it all be event triggered and watch for patterns and trigger actions so that when you find something important in the stream, it comes out and streams out to, say, downstream systems that do further processing or notifies someone that an important event happened. They need to come take a look. Or maybe it even calls back into the graph to implement an algorithm or update some data.
Can I dig into that a little bit? For those who are not familiar with Quine, thank you for giving the URL, quine.io. That will be linked in the show notes. There's, we're consuming messages from a Kafka topic, and then what? Is there an API? Is there a query language? Kind of maybe give us an example, a use case, and walk us through what that would feel like inside that graph processor there.
So a lot of cybersecurity use cases express themselves really well as a graph. Mm-hmm. And so it's a good domain to think about when you're trying to understand where's the bad guy, what are they doing? You're plugging into a Kafka stream, taking in a bunch of log data from routers, firewalls, endpoints, other things on your network that are collecting some telemetry data about what's happening. And then the real challenge of the cybersecurity challenge is really a data challenge. How do you put all those logs together so that you can understand what's going on? And what's going on is some interconnection in all that data. There's some process on a machine somewhere that read a file. So there's one event, a file read by a process that was started at one point in time. There's an earlier event. And that process, say, sent that file out a network, sent data from that file out a network. So exfiltration problem, bad guys stealing stuff, shows up in the logs with a couple events that happen spread out over time. When you watch a file be read, a process be started, a process send out data on a network, that network connection from the routers or the network logs going out the internet to a certain IP address. Each one of those is a separate event that shows up somewhere in your logs. And critically, they're spread out in time. What you
maybe
really
intentionally to not look suspicious, right? You space things out.
Yep. That's the advanced persistent threat problem.
Okay.
So the advanced persistent threat is the guy who's already in there. They're really sophisticated and they hide. They just lie low and slow.
You don't want to look weird.
Not making lots of noise. Don't want to look weird.
Exfiltrate a terabyte in the next 5 minutes. Somebody might see that.
That's right.
Yeah.
So instead, they just grab a little bit of data here, put it right over there, collect it from here, send it out there, spread out in time. and then buried under a mountain of regular, ordinary activity.
Mm-hmm. So in terms of anomalies and traffic, file IO, anything that you're going to have some time series signal, these threats know don't disturb that time series signal in any way that a reasonable anomaly detector is going to find.
Yep. Or maybe they know that you can only handle a week's worth of data at a time. And so, hey, they just do part one of their attack, one day, and then wait a week and a half, and then do part two.
There you go.
So they can hide in the data, even though their activities are being logged. They can't be processed because they have to be connected together in a stream fast enough to do something about it. And that's been the big challenge that has really, been a tough one to solve for a long time now.
Yeah. Okay. Absolutely get that. As a graph problem, could maybe be specific enough to tell me like what's a node and what's an edge? Kind of paint the graph for us in terms of that advanced persistent threat thing. We don't have a whiteboard together, but in words, what's that look like?
So draw on the whiteboard of your mind
Yes.
a node that represents, say, Microsoft Excel running on a computer. Okay. So there's a process called Excel. Mm-hmm. Sometimes Excel does some bad things, or people do bad things with Excel and make it do some things in the background, malicious macros and other activity. So you've got an Excel node in your graph, and every action that process takes leaves some trace in the graph. So it reads from a file, whatever file you're trying to open for your spreadsheet. There's an edge saying the event happened, that there was a read, and it points to another node that is the file. Mm-hmm. So process event file is your node edge node. Mm-hmm. So Excel reads a file. There's a node edge node. Excel writes to a file. Node, another edge, another node. And so that starts stitching together the pieces that draw a graph. And if you know to look at it, you can see the activity of everything Excel did represented by the nodes that are connected with an edge to that one Excel node right in the middle. So the malicious thing happens when, say, a bad actor puts a macro or some bad activity in a spreadsheet that they email to the CTO of the company. They open up the Excel spreadsheet, thinking nothing of it, and it reads an extra file on their computer. Just from their home directory, goes kind of checks what's there, says, what can I collect? So there's an edge to the nodes representing that file. Read those in, say stash them somewhere, stash the data by writing it out to a temp file. Just innocuous. Excel writes to temp files all the time, but that's another write edge to a temp file. And then later, the APT, the bad process, has been sitting there lying low and slow and knows to come in and look at that temp file. When it reads that file, it collects the data that was copied out of your private documents in your home folder by this malicious macro. So there's this coordination between the Excel process and the bad guy, the advanced persistent threat. And in a graph, it's connections from the file that was read from your home directory into Excel, a connection that writes it to a temp file, connection from there that reads it into the advanced persistent threat process, who then writes it out the network to some suspicious IP address. But you don't know it's suspicious.
We don't know. It's there's traffic to the internet happening all the time. But the point is, because of the connection between the process doing the write, reading the file in the temp directory written by Excel, that looks odd. Mm-hmm. And that's
you've got to put all the pieces together for it to look odd. Mm-hmm. Any one little connection could be perfectly normal. Excel reads files, no problem. Excel writes to temp files, no problem.
Yeah. Some process might read from a file and write that to a socket going somewhere on the public internet. Fine.
Yep.
That's incredibly normal, but it's that file is connected to Excel having written to it. Now that looks odd.
Yep.
Okay.
It's all the pieces. If you can put all those pieces together, then you've got the smoking gun. You've got the answer for here's the bad guy and here's the bad thing they're doing. But The problem is, while those logs come in real time, stitching them together into that graph that tells the story, that's the hard part. Turns out it's just this deep data problem, because not only do you have to stitch those together and do everything that we talked about in our little mental whiteboard, but you also have to handle all the mountain of other data that's coming through for every other process and every other bit of network traffic and everything else that's happening. So it's there, but it's so buried that most of the time we cheat. We say, I'll look at a little time windows worth of data, or have some sliding or rolling time windows, that let me simplify the problem. And that's what the bad guy takes advantage of, is the ways in which people simplify the problem, and then they end up not finding the threat. And a typical breach will cost you $4.5 million. So
okay, that's the running median breach cost.
Yep.
Okay, that's a number you would know.
it's some pricey log processing to not do.
Honestly, yes.
So the hard part there is consuming all that data fast enough and keeping up, and while putting the pieces together. And graphs have been good at visualizing that and putting those pieces together, but for a long time now, just their limits of scale has been the gating factor, has been the problem with why you can't really deploy that in a pipeline. And that's the problem we solve with Quine.
The problem of graph sharding is one, at least I know, has been a thorny problem. I haven't had my eye on the ball for a good 10 years, but I assume that's part of what Quine does?
It is, yeah. Quine's meant to run horizontally distributed. So you can add machines to support any volume of throughput. Our team has tested it running well above 1 million events per second, which is some pretty hefty data volumes. And the key functionality is, while it's ingesting that data at 1 million events per second, it's monitoring the graph that's being built. And it's monitoring it for any pattern that you want to find. So like in our APT example, you might monitor for communication between processes that uses a file like that. That's strange. And so you might want to know about every case where two processes communicate through a file in between. And so that's a much smaller list. And you can actually add some more things to the pattern. So also watch for if that communication led to data going out the network. So anything that represents the pattern that is the suspicious activity can be expressed, generally speaking, in a database query language called Cypher.
Okay, that was my next question. That's Cypher. So you express these. Well, I mean, in this case, they're anomalies in the cybersecurity case, but conditions that you would like to cause something to be produced to the output topic, because you said there's an input and there's an output, streaming output. Yep. So streaming output is produced as on the basis of a query selecting certain mutations of the graph or states of the graph, or am I thinking that's the right way?
Yeah, that's exactly right. Okay. So it's really monitoring the graph for whatever queries you want to monitor for. And Quine maintains what's essentially a materialized view of all the results as the graph is changing under the hood.
Okay. There you go.
And so using Quine is kind of this two-step process. We said it lives in between two Kafka topics. And so the first step is consuming from one and defining, here's a Cypher query that takes every JSON object, for instance, out of my Kafka stream and builds it into a small little graph pattern. That little graph pattern overlaps with the accumulating graph pattern from other events. So we're building a bigger, more connected graph over time. And then the second piece of the puzzle is watching that bigger, more connected graph for whatever patterns you're interested in. And every time there's a new match for that pattern, results stream out in real time.
Okay. And latency is, the ingesting of the new message plus a constant. There's no like occasional compaction finding of everything. It's just per message.
Right. Under the hood in Quine, everything is event driven. And so it's built on the actor model, which is oftentimes the foundation of a lot of stream processing systems. So that like teams will build their microservices oftentimes with actors supporting the real-time activity that's occurring under the hood. And so Quine is built on top of that actor model as well. So nodes in the graph correspond to actors that get distributed across any number of machines in a cluster. So a lot of your stream processing happens in the same or similar way as it would by sending asynchronous messages to actors, letting them do a little bit of work and communicating among themselves, passing messages back and forth. And when they're done doing their work, they send messages out. It's all of that typical kind of distributed system stream processing mechanism with a graph abstraction that lets us think at this higher level.
Right. Okay. So I'm curious about a few things, and I feel like there's still a lot for us to talk about, and I don't want to tax the patience of our listeners. So stick with me, everybody. I just want to dig into a few things. So, what's the basic approach to sharding this thing? I mean, I'm just sort of interested in that. And how does that relate to Quine? I'm assuming it's a Kafka consumer or something like that. Is there if we can just assume, there's a partitioned Kafka topic coming in, and we'll link to an episode in the show notes. If you don't know about Kafka, you probably do, but if you don't, we'll link to an episode where we talk about that. So Kafka partitioning plus graph partitioning, how's all that work?
So each member of a Quine cluster will plug in and consume from, say, one Kafka topic with many partitions. And so partitions get divided up among different members in a Quine cluster. They all ingest their data respectively. And then in Quine, we're representing potentially one big graph. And to take a graph and spread it across lots of machines in a cluster, you've got to make a choice. How are you going to chop up your data?
Right.
And what Quine does is it represents edges that are cut in half. So when you've got, like we were describing in our example, we've got Excel with this writing edge that points at a file. The nodes are the focus, and the edge gets cut in half into two half edges. And so the nodes might be distributed across different machines in the cluster. So you've got your Excel node on machine A, you've got your temp file located on machine B. And the edge that connects them saying this activity occurred and Excel wrote to that temp file, that edge is actually under the hood represented with two half edges that are stored with each node respectively. And so that
each half edge points to its sibling.
Yep.
Okay.
And then under the hood, there's the mechanics to kind of check each half edge and make sure that you've got a full connection. But the distribution model works in that way that nodes are really the focus of how it works. And you can spread out the nodes across many machines. And each machine is responsible for a subset of nodes in the graph. If there's connections between nodes that are on two different machines, their half edges point in each direction. And the system itself will guarantee that both half edges are there and checked accordingly.
And that it's traversable. And so there's some means of sharding, deciding this node lives here, that node lives there.
Yep.
But they're connected. We're not sharding subgraphs.
That's right.
You're traversing. Is there like a shared storage layer or in-memory thing by which all these are unknown?
So Quine focuses on that graph abstraction, and under the hood, it saves data durably in one of many different possible storage layers. I was
not half. I was 80% expecting you to say pluggable storage layer. I don't know why.
Pluggable storage layer. It's a good trend. It's we found.
Why would you not?
We found so many people who say, hey, this, some new technology is great, but I don't have the energy to go up against the bureaucracy of getting another database approved in our company.
Yeah.
And so
it's going to need to be Postgres. It's going to need to be Cassandra. It's going to need to be, it really has to be RocksDB or we have to die, right. Why should you have an opinion?
Yeah. So for Quine, what we need is fundamentally a key value store under the hood. If it's more powerful than that, great. We like to deploy with Cassandra or ScyllaDB, especially for large scale deployments. You've got network attached storage. You can have redundancy. You can replication. All of the things that you care about for high availability and production operation. Mm-hmm. That storage layer can be used by kind of a trusted team who knows their tool and wants to use their tool. And so we don't have to be opinionated about how the data is actually stored.
Okay. It feels a little cocky to think, I kind of get that. I know this is a complex technology, but I think you've painted the basics in a really clear way. And I see what it does. One can imagine these Cypher queries, Cypher, saying that correctly,
yep,
right?
That's right.
And that comes from
Neo4j.
Neo4j, yeah. Okay,
yep.
So that same, excellent.
Yep.
Those queries are being executed across the distributed graph and results produced to a Kafka topic, and then you know, hey, consume from that and turn on the klaxon or whatever it is that you want to do when the event happens.
The real goal there, what we wanted to enable is, we say high volume data comes in and high value data comes out.
Yes.
The idea behind our stream processing, probably if we're doing it right, should be, we can consume a huge amount, but we want to kind of climb the ladder of understanding to say that it's great that you've got all this low level log data, but what does it mean? It's like, great, several million events just occurred. So should I care? And that's a process of putting those pieces together to actually kind of interpret and say, well, these 5 things, when they happen together, mean that you've got this one really important event that happened. And so if we're doing it right, lots of data is coming in, and each step of our pipeline is probably stepping down the volume, but climbing the ladder of what this actually means to us.
And value, frankly. And I like that framing, and I'm just sitting here thinking, I think that describes a lot of analytics. I think it describes a lot of computation. I mean, maybe I have too much of an analytics lens on this, and I'm generalizing too much, but you've got a lot of bits come into your system, and the marginal value of each bit is very, very small, and you want a smaller number of much higher value bits to come out. I mean, that's maybe we'll just call that right now sort of a general account, almost like thermodynamic account of analytics.
I think it's a good one too. Especially if you think about different kinds of audiences, the people who care about results from analytics, kind of live at all different levels of an organization. And, engineers probably really care about the low level details, but then you've got executives elsewhere who are just like, is it good or bad? Should the light be red or green?
Exactly. And at some level and at some scale, did we spend less on security incidents this year than last year? Is the trend of the cost negative, much less the existence of the event, right?
Right.
At a certain scale, that would be kind of large scale, but exactly how much detail you're able to see. I mean, this is the perennial use of the term strategy and tactics. What constitutes one versus another just depends on scale. And same thing here, depending the level of detail we're interested in. But yeah, you are trying to do away with several orders of magnitude worth of the bits that come in and give much more valuable bits out in this based on these I guess graph traversals that you define.
Yep, exactly right.
Okay.
Yeah, it turns out the graph is this really tidy abstraction that can be general, can be flexible, so you don't have to pre-commit to a certain structure of what you're looking for necessarily. You can build it and change it over time. It's that no SQL kind of an approach where the schema is not a prior commitment. You don't have to decide what question you're going to ask, way in advance.
Okay.
You can kind of learn over
rewrite
time.
My consumer? That's like there are various kinds of JSON objects that I'm pulling in, and I have my persistent graph, but I can say, oh well, there's this new field. I want to start connecting edges based on that. I can just sort of do that and it's fine.
Yep,
Love
exactly.
it.
Add a new stream, some additional data to enrich what you already have that wasn't available before, you didn't know about it before. Start streaming that in to even the same graph. Make your graph richer so that you can answer questions better, and produce richer results that come out.
So that's Quine and graph analytics. Tell me about this dot.
I can tell you about that dot, but our use of
we are not going to cut that out. That's an embarrassing error. We're going to keep it, I think, for the sake of integrity. Tell us about that dot, please.
That dot is a young company trying to help folks commercialize or kind of like deploy in a commercial environment these kinds of applications. And so taking Quine, scaling it to huge data volumes, applying it in specialized kind of environments. Quine is a back pressured stream under the hood. And that's some internal technical detail that basically means at the far end of the picture, it can remain stable in an extremely resource constrained environment. So if you need to run a system like this on the edge in, say, a couple 100 megabytes, like you need to run it on a Raspberry Pi, on an airplane, or a boat, or some kind of specialized environment that does not have a whole data center available to it, Quine can scale down to that kind of micro deployment and still do all the same stuff that we talked about. Not quite as fast, mind you, but
of course,
still do everything and remain stable and provide those kind of answers. And so that dot helps companies deploy in those kind of environments, and even to understand how their particular data, when you think about it as a graph, and when you take a little bit of kind of graph experience to existing data that you wouldn't normally think of as a graph, it's pretty transformational how that view on data just unlocks a whole new understanding of what you can do, especially when you have this efficient event triggered processing on it. And you can have a graph that can give you this pre-processing step for some other downstream, say, expensive systems that you want to be able to move some of the analytics that happen at the very end upstream so that you can have some answers earlier. You can maybe filter down your data and keep the full volume of that high volume coming in, keep that from having to go into the expensive systems downstream, and do some of that pre-processing with Quine. So our team does a lot of work with a bunch of companies around the world on that kind of a focus.
Where that pre-processing is this profoundly stateful finding of connections between events that is best expressed mentally as a graph and a query over a graph. The kind of cybersecurity problem you framed, it in the scope of a conversation in a podcast, I can't imagine trying to do that some other way.
Yeah.
That would just be bad.
I'd say the state of the art, and there's probably lots of teams right now who are doing some version of this. They're consuming that kind of data coming in, but then what they're looking for, the pattern that they're looking for, ends up being a collection of microservices with lots of different data storage engines, usually key value stores, that are trying to put the pieces together. So you have a key value store in your data pipeline that is just trying to hold on to every process you see, because you might need to connect it with an event later, and another one holding onto the files, because you might need to connect it to an event that connects to a process.
Yeah.
And so what
let's
tends
stand
to happen,
up a new microservice and table or whatever abstraction in our data store. Let's do all that for every new kind of thing that we want to do when we just meant to express a new node, an edge, and a graph. Yeah,
this is why data engineers have among the lowest job satisfaction in the industry. Is because, there's a new requirement coming in from the business that we need to tweak the pattern we're looking for. All right, set up a team to go stand up a new microservice that's going to, handle the combination of these other two things and have it ready to serve when the data flows through. And
yeah, it feels like shoveling sand from one pile to the other and then that pile back to the first. It does not feel good. It's, Job dissatisfaction in DevOps is caused by YAML. Data engineering, it's caused by this kind of thing. That makes a lot of sense. That dot. This dot sounds like it would be sort of some sort of front end web JavaScript play. Different thing, not you at all. That dot, at the risk of being reductive, you help people have I assume a fully managed version of sort of the SaaS version of this, because it sounds kind of hard to deploy. I mean, I would, if I needed this, I'd be grateful that someone was willing to host it for me.
Yep. Yeah. So we work on all of those fronts. We don't currently have a SaaS offering quite yet, but there's one in the works. It's just between me and you.
All right, good. We won't put that on the podcast. Well, it's there, but that's excellent to hear. Yeah. And I don't know if there's anything we can link to, but we'd love to. So.
Yeah. So we've been working on this for a long time. We're really grateful for support from DARPA through a lot of the research and development phases of this. It's we're at about 9.5 years at this point. So it's been a long journey with some of the smartest people in the world. And we managed to roll up a whole bunch of them together at that time. So that's been a really fun activity.
My guest today has been Ryan Wright. Ryan, thanks for being a part of the Real-Time Analytics podcast.
Thank you, Tim. If anybody wants to try out Quine, it's free to use. You can find all the docs and the downloads at quine.io.
And there you have it. If you feel compelled to help us spread the word and grow the real-time analytics community, you can give us a rating on Spotify or Apple Podcasts or wherever fine podcasts are sold. If you're watching us on YouTube, hey, subscribe and, of course, hit that notification bell. And you can always share your favorite episodes on LinkedIn or Twitter or wherever it is you do social media. Thanks, and I look forward to talking to you in the next episode.